Welcome to the deep dive. So whenever you see one of those massive wind turbines, standing on a hill or way out at sea, they look almost deceptively simple.
They really do. Just a huge tower, three blades, spinning pretty slowly.
Exactly, like a giant lazy fan. But if that's all you see, you are missing, one of the most brilliant applications of fundamental physics that's powering our world today.
That visual simplicity hides a staggering amount of engineering. We've pulled together a stack of sources today that take us right inside the engine room of wind energy.
And that's our mission for this deep dive, right? To get a fast but really thorough understanding of the physics, the unseen forces that turn moving air into electricity.
We're breaking down the science of the spin because this entire industry, which is a huge and growing part of global power, it runs completely on motion and magnetism.
Yeah.
Not fuel, not fire.
Just physics, pure physics and massive clean energy action.
Precisely. Let's jump right in.
Okay, so let's start at the absolute beginning. The wind itself. A wind turbine is, at its core, a machine that's just converting one type of energy into another.
Right. It takes the kinetic energy from moving air and turns that into rotational motion.
Which then spins a shaft, turns a generator, and boom, electricity.
And, understanding that initial kinetic energy is the foundation for everything. The total power available depends on really three things: wind speed, air density, and the area the blades sweep.
But two of those are more or less fixed, aren't they? Air density doesn't change that much, and the blade size is set.
Exactly. So that leaves wind speed as the single most critical variable.
And this is, I think, the first big aha moment. The relationship between wind speed and power isn't, it's not linear. It's not one-to-one.
Not even close. It's cubed. That's the physics rule that matters most. Because the energy is proportional to the cube of the wind's velocity, the returns are just exponential.
So what does that mean in practice if you double the wind speed?
If you double the wind speed, say from 10 miles an hour to 20, the energy in that wind stream increases by a factor of 8.
8 times. Not double, not triple. 8 times the energy.
It's staggering, and it completely changes the economic equation. It's why an operator will always choose to spend more money to build in a slightly windier location.
Because the payoff is so massive.
It's an exponential return. That's why you see turbines on high plains, on coastlines, and especially that huge push to build them offshore.
They're chasing that cubed relationship.
Absolutely. They're chasing the faster, less turbulent winds to get that exponential energy return.
Okay, so that covers the energy in the wind. Now let's get into the engineering, which I find fascinating. Because they aren't just paddles being pushed, are they?
No. And if they were, they would be terribly inefficient. This is the biggest misconception out there. People think of them like a child's pinwheel, just being pushed by drag.
But that's not what's happening.
Not at all. Modern turbine blades are expertly shaped like airplane wings. They're airfoils.
So the same physics that keeps a jumbo jet in the sky is what's spinning a wind turbine. How does that work for rotation?
It's all about Bernoulli's principle. The blade is curved on one side and flatter on the other, so when wind flows over it, the air on the curved side has to travel farther faster.
Okay.
That difference in speed creates a pressure difference. You get low pressure over the fast-moving air on the curved top and high pressure underneath.
And that pressure difference is what we call lift.
Exactly. The low pressure literally pulls the blade forward. And because the blades are mounted at an angle, the pitch, that lift force, is translated directly into rotational motion. The whole system is lift-driven.
Wait a second. If the force is lift, which, like you said, makes planes take off, why doesn't the entire turbine just get pulled out of the ground?
No, that is the ultimate engineering challenge. And it's why these blades are so incredibly sophisticated. They have something called twist.
Twist.
Yeah. The part of the blade near the hub is moving slower, so it's angled steeply to catch the wind. But as you go out toward the tip, which is moving much, much faster, the angle gets shallower.
So the angle is changing all the way down the blade.
Correct. This twist ensures that lift is generated efficiently along the entire length, and critically, it directs that force into torque.
Torque, the twisting force. That's the key to the conversion.
That's right. You're turning linear motion, the wind, into angular motion. And the torque you get depends on that lift force and, of course, the length of the blade.
So longer blades mean more torque. Why not make them a mile long?
Well, there's always a trade-off. Longer blades give you more torque, yes. But they're also exponentially heavier. That adds mass, inertia.
Meaning they're harder to get started and harder to support.
Precisely. You need more wind just to get them moving. So it's this incredibly delicate balance between aerodynamic shape, material strength, and weight. We're talking about blades longer than a football field made of high-tech composites.
That perfectly sets up the next step. We've used physics to create powerful, controlled rotation. How does that spin become electricity?
This is where we see that beautiful intersection of motion and energy, all governed by Faraday's law of electromagnetic induction. This is what's happening inside the generator.
Let's just break down Faraday's law for a second. You need a changing magnetic field to create a current.
That's the whole principle. The rotating shaft is connected to a huge array of magnets. As they spin past fixed coils of copper wire, that constantly changing magnetic field forces the electrons in the copper to move.
And moving electrons are, by definition, an electric current.
And that's the clean part. The power source is just motion. The conversion is just physics. No combustion, no smoke.
And this brings up a big design choice, right? The sources talk about geared systems versus direct drive.
A very significant divergence, yeah. The traditional geared systems use a gearbox, kind of like the transmission in your car.
Why do they need one?
Well, the blades turn very slowly, maybe 15, 20 times a minute. But the generator needs to spin at thousands of RPM, so the gearbox multiplies that speed.
But a gearbox has a lot of moving parts. That sounds like a point of failure.
It is. It creates friction, which means you lose energy as heat, and it requires a lot of maintenance. So the alternative is the direct drive system.
Which gets rid of the gearbox.
It connects the slow spinning rotor directly to the generator. But to make enough power at that slow speed, the generator itself has to be absolutely massive, a huge ring of hundreds of permanent magnets.
Which would be incredibly heavy.
Exactly. They're much heavier, but they're also more efficient because there's less friction, and they are way more durable. That's why you see them becoming the standard in the newest, biggest offshore turbines.
Okay, so this brings up a really important question. If the wind is free, why can't we just build a turbine that captures all of its energy? Every last bit.
The laws of physics have a very firm answer to that: no. And this brings us to one of the most fundamental rules in wind energy, Betz's law.
What does Betz's law say?
It was figured out by a German physicist, Albert Betz, back in 1919. It states that no wind turbine, no matter how perfectly designed, can convert more than 59.3% of the kinetic energy in the wind.
59.3. That is a very specific number. Why? Why can't we get that other 40%?
The reason is actually pretty intuitive when you think about it. To get energy from the wind, you have to slow the air down.
Right.
But if you took out 100% of the energy, the air would come to a complete stop right behind the blades.
And then it would just pile up. No new wind could get through.
It would create a blockage. The whole system would just stall. So for the turbine to keep working, the air has to keep moving out the back. That leftover energy is the price of continuous operation.
So it's not a design flaw, it's a law of nature.
It's a necessary trade-off. And modern turbines are incredible. They consistently hit efficiencies between 40 and 50%.
Which is actually really close to that theoretical limit.
Impressively close.
Yeah.
It just shows how well we've mastered the aerodynamics and the mechanics.
Okay, let's move from theory to the real world. Wind is constantly changing. Gusting, shifting. These huge structures need some very sophisticated controls to stay safe and efficient.
Constant management, absolutely. They have two primary controls. The first is yaw control.
Yeah.
That's just turning the whole top part of the turbine, the nacelle, to make sure the blades are always facing directly into the wind.
That seems pretty basic.
It is, but it's crucial. If you're off by even a few degrees, your power output drops. The second, more dynamic system is pitch control.
And pitch is the angle of the actual blades.
Correct. The system is constantly adjusting the angle of each blade on its axis. In low wind, they angle them to maximize lift. In high wind, they angle them the other way to spill some of that energy and keep the rotation stable.
It's like a constant dance to stay in that perfect sweet spot.
And when the wind gets too extreme, say over 55 miles an hour, the safety systems kick in. They use that same pitch control to feather the blades.
Feather them.
Turn them completely edge-on to the wind. It minimizes all the forces, stalls the rotor, and the brake locks it down to prevent damage.
Now let's connect all this to the future, which is offshore power. What are the specific physics advantages of moving turbines out to sea?
It's all about fluid dynamics. Wind over the ocean is just faster. There are no hills, no trees, no buildings to create friction and slow it down.
More speed, and as we said, that means exponentially more energy.
And second, it's more stable, less turbulence. So the turbine operates at its peak efficiency for much longer stretches of time.
But you're also introducing a whole new set of challenges from ocean physics: waves, corrosion.
And one of the biggest challenges is something called structural resonance.
What is structural resonance?
It's when the frequency of an external force, like waves hitting the tower over and over, matches the natural vibrating frequency of the tower itself.
So the tower could start to shake itself apart.
Exactly. A small repeating push can cause the vibrations to get bigger and bigger until you have a catastrophic failure. Engineers have to design these things so their natural frequency never aligns with the forces of the wind or the waves.
And that's what's driving the next wave of innovation.
Precisely. Lighter, stronger composite materials, taller towers to reach even stronger winds, and the real cutting edge floating offshore turbines.
Not even fixed to the seafloor.
Nope, floating. Which requires a whole new understanding of ballast and tethering physics just to keep them upright and stable in extreme seas.
So, to recap, the next time you look at a turbine, you now get what's happening. The 8 times energy rule, the use of lift, not drag, Faraday's law turning motion into current, and that hard limit from Bess's law.
Every single piece of that technology is a real-time testament to how understanding fundamental physics is reshaping our energy future. It gives you a whole new perspective when you see one spinning.
And before we go, here's a final thought for you to explore. We mentioned structural resonance, that dangerous alignment of frequencies. I want you to consider the materials science needed to solve that. What kind of advanced composites, what kind of internal damping systems, or maybe even active computer-controlled systems are required just to let a skyscraper-sized machine stand up to the relentless physics of the ocean and gale force winds without collapsing. Just think about the sheer scale of the engineering needed to keep that structure perfectly steady, miles out at sea.